Hi, today we are going to look at adding and scalar multiplication of vectors. So you should have a pretty good understanding of what addition and scalar multiplication of vectors is already, because it's basically addition and multiplication of numbers, which we've done. So to show that, let's have a look at the number line, which we've got up at the top. We've got it spanning from -5 to 5. So if I wanted to draw the number 2 on this number line, I could represent it as a vector. So to show that, whoops, we've got that happening. We've got a vector here. Okay, so that's the number 2. Now, if I wanted to add 1 to it, all I need to show is another vector sort of going on the end of it, right? So we've got another 1, and our end result, 2 plus 1 equaling 3, is just that end vector where we add from the start until the end. So we end up with a vector of 3. So if we look at our Cartesian plane now, which is our two-dimensional representation, let's label our vectors down here. We've got vector A, B, and C. Let's say I wanted to add vectors A and B together. So to do that, I'm just going to draw vector A, which is this one here. We've got 1 across and 2 up. So that's my vector A. Now, what we mentioned in the previous video is the only two characteristics of a vector that matter are its length and its direction. It doesn't matter where the vector starts. So what we're going to do is we're going to take vector B and we're going to move it up so that the tail of it sits on the tip of the arrow. So just like we did for here with the number 1, we moved it so that it was on the tail of it, this end of it was on the tip of the first 2 vector. We're going to do the same here. So we're going to move the tail. We're going to move the tail so it's starting here, and we're going 4 across in the negative x direction, like this. So that is exactly the same way as we did it on the number line. It's just now we have 2 dimensions. Now if we want to add these things together, we're measuring from the start of the vector complex until the end of the vector complex. So to do that, just like we did up here where we drew an arrow, we just draw an arrow from the start to the end, and that is our end vector. That's A plus B ends up being that point there. So we can write that as the vector A plus B, and we can even say the direction that it's going in, right? It's going -1, -2, -3, and it's going up 2. So we can say that's the end position of the vector A plus B. Now with these vectors, you don't need to just have 2, you can have more than 2. So we can add 3 vectors together. Let's show that. So if we were to do A plus B plus C, we can draw that on there. So I'm just going to use black so that it's a little bit quicker. So we've got A, we've got B goes across 4, and we've got C goes down 3 and across 3. So we've got down 3, 1, 2, 3, and across 3. And we end up with the vector, so from the tail of the complex to the tip of the complex, it travels in that direction. So that would be 0 in the x direction and -1 in the y direction. Now, as adding numbers, so using our vectors in 1 dimension, adding them in a particular order doesn't matter. The same thing happens with vectors. So if I did 1 plus 2 as opposed to 2 plus 1, I'm going to end up with 3. If I did this in a different order, let's just do B plus A in this instance, I should end up with the same thing. I should end up with this vector here. So let's trial it out. So we've got our B vector first. We're going across -4. And then if we want to add a, we're going across 1 in this direction and up 2 in that direction. If we draw our resultant vector, we are going -3 in the x direction and 2 in the y direction, which is exactly the same as what we had here. So addition, different orders, again, doesn't matter for vectors. So that's addition of vectors. We can also do the scalar multiplication of vectors. Now, what scalar means, scalar, scale, it means that we're scaling the vector to make it either bigger or smaller. So again, we've done this with one-dimensional vectors before, and this can get a little bit messy, but we got 0, 1, 2, 3, 4, 5. So if I had the vector 2, and I multiplied it by 2, I'm making it twice as big. So I'm scaling it up by a factor of 2, and I'm going to end up with a vector of 4. If I was to do 2, which is my original vector, times a half, I'm going to shrink it by a factor of 2, or I'm going to condense it by a factor of 2, right? So if you end up with a number smaller than 1 that you multiply by, it's going to shrink. If the number is bigger than 1, it's going to get bigger. If you multiply 2 by 1, it's going to stay the same length. You're not going to scale it at all. So we call this number that we're multiplying by a scalar because it's the thing that scales the vector either bigger or smaller. So let's have a look at this in 2 dimensions. So we've got, let's do the vector A. Now, if I was to multiply a by 2, we can write that as 2a. All I'm doing is I'm scaling it up by a factor of 2. So I'm drawing, that's 1, and that's another one. So I can say that 2a is equal to, it's going 2 across, and it's going 4 up, 2, 4. And that's it. If I was to do it by a half, we can also do that. It's going to look a little bit difficult graphically, but we've got something like that. And what that's going to end up as, if I write it as half a, we're going about half across. So we can either write that as 0.5 or a half, and we are going 1 up. Now that's a little bit hard to see in this diagram, and there are numerical methods that we'll introduce to make it a lot easier to do this, but that is essentially the feature of these things. Now you can expand this whole operation where you can do addition and scalar multiplication. So I'll show you one example of that. If you had something like 2a plus 1/2 b. So we can draw our a vector is here. If we're doubling that, we're going to go all the way up there. So that's my 2a. Half b, b is the full one, so that's a full b. Half b is going to be half the length of that. So if I want to show the end result, we've got from the tail to the tip. And you can see that we're going 0 across and we're going 4 up. And that is the result of 2a plus half b. So we've looked at addition of vectors and the scalar multiplication of vectors, and that's all for this video. Thanks for watching. This video accompanies a worksheet series that aims to develop conceptual understanding with vectors. If you'd like to access the worksheet, click in the description below.